Hi, the purpose of this lecture segment is to explain how to convert ordinary numbers written to base 10, we'll just be dealing with integers, to binary, or to numbers written in base 2 just using zeros and ones. So base 2 of course is very important because it's the way in practice that computers store numbers. 1 stands for off. 0 stands for off and 1 stands for on, although historically some computer hardware systems have used other bases. For example, base 16 was used by IBM, and a Russian computer was devised to use base 3. Anyway, binary for us will be important. Also for practical purposes to do things by hand, we'll be using binary to do a quick way of exponentiating numbers. And when we come to discuss linear codes, we'll do it entirely in binary or base 2. We'll be working with matrices over the field of 2 elements. So I want to explain this process with a number of examples. And just to sort of explain what we're all about, let me just take a small number at random, 23 I've chosen. So if we just take the ordinary number 23, first of all, this is of course written in base 10 in the usual Arabic notation that we're very used to today, although dating may be from India in the 5th century. What does 23 mean? It means 2 times 10 to the power 1, of course, 2 tens, plus 3 units. That's 3 times 10 to the 0. So the idea is we're expressing integers as sums of powers of 10 with these coefficients that can go between 0 and 9 inclusive. But we want to write this in binary to base 2. So that means we have to express the same number as a sum of powers of 2. So the way one can do it with a simple example like this is first of all sort of squeeze the biggest power of 2 you can find inside 23, that's 16 of course, and then add on powers of 2 until we get to 23. But the difference between 16 and 23 is 7. 7 is, we need what? 7 is 4 plus 2 plus 1 unit. So written out in terms of powers of 2, that's 2 to the power 4 plus 2 squared plus 2 to the power 1 plus a unit, which is 2 to the power 0. I haven't put all the powers. There's a missing, that there would be 2 to the power 3 here, but of course that's missing. So if you like, the coefficient of that is 0, and the coefficient of these is just 1, all these. So that's telling us that 23, how do we write it then in binary? Well, let's start with the 16 to begin with. If we were just writing 16 in binary, it would just be 2 to the 4, and that's easy to remember. It's actually 1 with 4 zeros. I'll write them very lightly. If you have 2 to the power k, say, you need a 1 with k zeros in binary. But we haven't quite got that. We've got to add on this stuff here. So that doesn't affect the second digit, so I can fill that in as a 0. But we've got 2 squared, so this becomes a 1, this becomes a 1, and this becomes a 1. So 23 expressed in binary is that number. So for clarity, I'll rewrite this 1, 0, 1, 1, 1 to base 2. Put in the 2 for emphasis. This is really to base 10, but we don't normally bother to put the subscript in. So that's the idea. That's writing the ordinary number 23 in binary. This is telling you it's 1 lot of 16, 1 lot of 8, so 1 lot of 16, no 8s, 1 4, 1 2, and a unit. But it's not a very systematic method because it takes a bit of time to sort of find the biggest power of 2 less than a given number. So here's a more systematic way. So I'm going to give this more systematic approach, which you can do really without thinking. It may be a bit long-winded at times. But let me illustrate this method. It's just going to consist of repeated division by 2. And it has the difference that whereas in this method we were really constructing the numbers from the left, we started with the 16, which gave us this 1 in the sort of fifth position. The new method will actually build up the bits or binary digits from the right-hand side. So in this more systematic way, I'm going to do a different example. So let me choose 2021. Okay, I should be teaching in this year, so it sort of proves that I'm in the right decade at least. Actually, I am recording this in 2020, but nonetheless. Let's try and express this in binary. So the way we do this is we just keep dividing by 2. So, but we don't want fractions, so we may need remainders, which can either be 0 or 1. So this is twice times 1010 plus a remainder of 1. And then we take this quotient 1010 and we divide that by, I don't normally bother with the commas, to be honest, it's just for clarity. 1010, of course, that's twice 505. And there's no remainder here because this is an even number, so it's divisible exactly by 2. And then we just keep going. 505 is equal to twice times, well, it's 252, but there's a remainder of 1. And then 252, you bring the 252 to the left, and this is equal to twice. This is again an even number, so the remainder is going to be 0, but it's twice. You can use really long division here if you like. So 2 into 2 is 1, 2 into 5 is 2, 1 left over, so it's twice times 126. Good idea to do this all by hand, given that the number's not very large. 126 is equal to twice. This is an easy one, it's just 63. No remainder. And then I can keep going. 63 is equal to, but there's a sort of trick here, because you can pretend you've sort of paused here, and I found the first few digits. This one here will be the digit on the extreme right-hand side, because this is an odd number, so there's going to be a 1 unit on the right. And we found the working from the right, we found the first, second, third, fourth, fifth digit. And then, if you like, if I knew the binary expansion of 63, I can just put that further to the left. But I do separately know, sort of secretly know, the binary expansion of 63 without applying this method, because 63 is 64, which is 2 to the power 6 minus 1. And 2 to the power 6, remember, I'd write that in binary as 1 followed by 6 zeros. So that means 63 has to be 6 ones in binary. So if I were to apply this method to 63, I just get 6 lots of 1s. So I'm going to get 1 as a remainder at the next step, and then another 1, 1, 1, 1, 1, and then I finished. You see, I can do the first step to convince you that 63 is 2 times 31 plus the remainder of 1. And you're just going to get all the powers of 2 minus 1 in this column as the quotients. And the last line is going to be something like, you'll end up with a 1 here as the quotient, and 1, of course, is twice times 0 plus a remainder of 1. You'll always get this on the last line, so you'll always get a 1 at the end, which is necessary because when you express the binary, the answer, you always got to start with a 1. So let's just record the answer. And the answer, therefore, is that 2021 expressed in binary is, we're going to read up from the bottom. So it's 6 ones. That gets us to here, and then it was 0, 0, 1, 0, 1. So that's what 2021 is to base 2. Remember, the 1 here is telling you this is an odd number, and that corresponds to the 1 at the beginning, whereas the 1 here on the extreme left corresponds to the final one here. So you must remember always to, if you're writing from left to right, you have to read from bottom to top in this method. That's the systematic way of finding the binary expansion of a number expressed originally in base 10. Now, could always do, let's just, if that is not clear, let me just do the example of 23 using this systematic method, just to double check we understand the method. So 23, if we divide repeatedly by 2, it's 2 times 11 plus 1. 11 is equal to 2 times 5 plus 1. 5 is equal to 2 times 2 plus 1. Then we're getting to the end. 2 is equal to the quotient. 2 is equal to 2 times 1 plus 0. And then finally, as I said before, the last line is going to be quotient 1 is equal to 2 times 0, obviously, plus 1. Okay, so this one tells you, as we already knew, of course, that 23 is equal to, read up from the bottom, 1, 0, 1, 1, 1 to base 2, which is what we found before. So that is the systematic way of finding binary expansions. Let me digress here because I found a number which is familiar to me in the workings, 252. So I just want to say something about that. So this is a digression, nothing to do with binary, but it's worth saying it because this relates to a binary coefficient, sorry, a binomial coefficient. You see 252 I happen to recognise because it's 10 choose 5, which I write like this. It's a binomial coefficient. You might prefer to write it 10C5 or some variant of that notation. And it's the number of ways of choosing 5 objects from 10. 5 objects from 10. Written in shorthand like that. I mean, the definition of this would be 10 factorial over 5 factorial times 5 factorial, or in practice that means if you take these two, it means 10 times 9 times 8 times 7 times 6 over 1 times 2 times 3 times 4 times 5. And if you check, you'll get 252. Equivalently, I just want to say a bit more because binomial coefficients will be important at times for counting in this course. So it's called a binomial coefficient because it's one of the coefficients you get when you do a binomial expansion. In this case, 1 plus x to the power 10. So 1 plus x to the power 10 is going to be 1 plus 10x plus, that's going to be 10 nines over 2, that's 45x squared, and you keep going, and you'll get the coefficient of x to the fifth will be 252, and then of course you can keep going, and you'll end up with x to the 10. It's also, you also see this number in the middle of Pascal's triangle because the binomial coefficients can be read off. They're tabulated by Pascal's triangle, which I won't write down, but this is one of the sort of middle coefficients you'll find in the 10th or 11th row of Pascal's triangle. Let me now give some exercises on the binary. So that's the end of the digression. Let me give some exercises. Let me give 2 exercises, one of which I'll do on the binary business. So exercises, one I'll leave for you, and maybe it will be in a quiz, is suppose we take the number. So the exercise is simply to express the following number, 65,000, this time I won't put the comma in, 537 to base 2, or in binary. Now it turns out this number is a very special number. It's called it's a prime number, and it's a special prime number. It's an example of what's called a Fermat prime number. I'm not going to tell you what that is, because if I did, it would give the game away and it would help you do this exercise. I just want you to do this exercise using the systematic method, which I just taught. And then you can look up Fermat prime. That's the first exercise. I'll leave that to you. The second one is going to be a worked example. So the second exercise is going to be the following. How many bits? A bit is, remember, a binary digit. So how many binary digits are needed to express the following number in binary? And this is just an example I happened to use last year, so I called it n for convenience, but this is actually the number 8,293,000. I don't know why I chose this number. I don't know if it has some special reason. How many bits are needed to express this number in binary? Okay, now it's important to realize here that I'm not asking you to expand this in binary. You could use the systematic method. It would take quite a long time, probably 2 sheets of paper. I did try and do this last year, but I had to give up because it was taking too long. But I'm actually only asking you, how many bits do we need? And we don't, to answer that question, we don't actually have to do the calculation. You see, the way you do this sort of question, and we will need to answer questions like this for certain practical exercises, for example in linear codes, to answer this, it's very helpful to realize that 2 to the power 10 is 1024, and that's a good higher power of 2 to remember. It's easy to remember. And incidentally, I want to get towards 8 million, so I'm going to have to start by squaring this. So it's a good idea to write this as 1000 plus 24, because then when I square it, and when I square this, I'm going to get 2 to the 20. I can just use the binomial expansion. This is going to be 1000 plus 24 squared. Let me write that. And you just use the binomial theorem on this. Here we've got to the power 2, not to the power 10, so it's a bit easier. So it's just 1000 squared, which is 1,000,000. And then it's twice the product, which is 48,000. And then we're going to have plus 24 squared. Well, I don't really care about 24 squared because that's going to be fairly small, so less than 1,000. So I'll put 24 squared, but I'm not going to remind myself or calculate that. So this is actually equal to 1,048,000 commas in something, 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 which I don't care about. Because I want about 8 million, so obviously it makes sense for me to multiply this by 8. So 2 to the 23, what would this be? This would be 8. This is 2 to the 20 times 2 to the 3, so I just have to multiply this by 8. So that would be 8 million. Now 4 8s are 32, so I'm going to put a 3 there, and then I don't care what comes afterwards. The 8 8s are 64, that won't affect the 3 here. So you see we've already got a number which is bigger than n. If you look and see what n is up here, we've exceeded it. So we can now say that, of course, 2 to the 22, that's going to be something like 4 million something. That's certainly less than n. So n is greater than this, in fact, so I can write greater than or equal to, that's not wrong. And n is less than 2 to the 23. So if you remember the way we did this for, just remember, let's compare this with, what did we have? We had 2 to the 4 is less than or equal to 23, which is less than 2 to the 5. And to express 23 in binary, we needed 5 bits. So by analogy, we're going to need 23 bits. So that means that we need 23 bits. That's the answer to the exercise. Even if n were equal to 2 to the 22, we would need 23 bits. But if n is equal to 2 to the 23, we would need 24 bits. That's why the inequalities are like this. The first one is the last one is strict. We can have equality in the first one. So to find how many bits we need to express a given integer in binary, we have to sandwich it between two adjacent pairs of 2, and then we can read the number of bits off from the exponents. Okay, that's the main thing I want to say about binary. Just try the exercises and see if you can replicate this method.